All right, thanks, Pranoy. Good morning, everyone, and welcome to this week to our CAE-CET seminar series. It's my pleasure to introduce to you today to Hossein Roghani, who is a student in our department. He works with Dr. Nani, and he's a member of a couple ECI committees, and his research basically focuses on using non-metallic reinforcement on concrete structures. And today I think he's going to tell us a little bit more about his work on pre-engineered applications of this non-metallic reinforcement. So with that, Hossein, welcome to the seminar, and we are looking forward to your presentation.
Okay, hi everyone. Hope you can see my screen now, the presentation, if you can confirm it.
Yes, we can see it.
Okay, so today I'm going to talk about first, let's introduce myself again. I'm Hossein Roghani. I'm working with Dr. Nani for my PhD on non-metallic reinforcement and FRP rebars at the University of Miami. Today I'm going to talk about pre-engineered applications of these rebars, the non-metallic reinforcement, and the focus of the talk is the fiber reinforced polymer rebars and the meshes, so-called FRP, internal reinforcement, and I will cover two in-progress research which are conducted at the University of Miami, Structures and Materials Lab. The first project that is the main leg of my dissertation is the shrinkage cracking control of slabs on ground, also called slabs on grade, that is in the scope of pre-engineered applications of the FRP. And the second project, which is the surface profilometry of the FRP rebars to characterize the surface profile rebars effect on bond strength and bond behavior of the concrete and the rebar. And I'm going to cover the reason why we are doing this research, what we have in the literature, where the research gap is, what innovations we have conducted, what are the outcomes and expectations, what the plan is, and what we currently have as the result. Because these research are not completed here, we are struggling and we are working on them. And actually the second one, the surface profilometry, we have started it recently with a collaboration with the University of Sherbrooke in Canada. So they are kind of premature research, but still we have some result to talk about them here. First, since the topic is the pre-engineered applications, I want to tell you what are the pre-engineered applications here. Here it means applications in which there is no real need for a comprehensive design, and the contractor just follows a prescriptive guideline to come up with the geometry of the concrete element and configuration of the required reinforcement. That reinforcement can be rebars or the meshes, steel, steel FRP or whatever. And the prescriptive guidelines that I mentioned can be a table in which you can find the geometry of your application. For example, if you are casting a slabs, here you can see the application, a slab on ground grade construction. You can, for example, find the geometry of your slab in terms of the thickness and also the type of reinforcement you are going to use, and just check the table, come up with the spacing of the reinforcement, the diameter of the reinforcement, and you do not need to go back and forth for the design and see if the design works. So you have a table that can help you to follow your design. And as the example of these pre-engineered applications, I can say the first one as kind of main one in my dissertation is the slab on grade. The slab on grade is defined as a directly laid slab on the earth for supporting the structural elements and the walls. As the name suggests, a slab is a single layer of the concrete, several inches thick. The slab is poured thicker at the edges to have a kind of restraint to form an integral footing. It's a footing for your slab. And you have the reinforcement, which add a little bit in terms of structural strength, but that's not the reason. I can say the main reason is to control temperature and shrinkage crackings, which is the main concern in this research. And the other application can be the high-rise building balconies. So in the balconies, we have some sort of reinforcement that we can, hopefully at the end of this research, we can confirm that contractor can use this type of reinforcement instead of the previous reinforcement they have. Okay, and currently they are using a steel reinforcement in the slabs on ground. The steel reinforcement has several advantages in this case. It helps to control the cracking, which is I can say is the main reason you have the reinforcement there. And also it can increase the joint spacing. It can restrain the curling, add structural strength, but it's not really the case. And also reduce the slab and joint maintenance and many other advantages that you can see here. Okay, and okay, as I told you, in this research, we are really going to concentrate on the shrinkage control. So the reinforcement in these applications, they are doing many stuff. As I told you, they are increasing the joint spacing, restraining the curling, but the main thing is to control the shrinkage cracking. This reinforcement prevents development of shrinkage cracks, and some main reasons of the concrete shrinkage are the settlement of the solid particles you have. I mean, the aggregate, the fine and coarse aggregates that you have inside your concrete. The next thing can be the bleeding, the evaporation of the water from the surface that is the outcome of your environmental condition, the combination of the wind, the ambient temperature, the relative humidity, and the concrete temperature itself. But that's not environmental, so it's related to concrete. And also capillary action and also the surface finishing. It depends how good you finish the surface, in which direction you have finished the surface of a concrete. All this stuff can cause or prevent the shrinkage cracking and shrinkage behavior for concrete. This research aims to provide alternatives to address the challenges related to a steel reinforced concrete shrinkage, which have been studied for more than half a century. I can say maybe for more than 60 years that they are working on the shrinkage issues. The shrinkage shrinkage cracking not only affects aesthetics, but more significantly increases the probability of reducing concrete durability and the structural service life, which is the main concern for other people. Maybe when they see the cracks or just they see something on the surface of their structures, they may have some concerns, and also they just feel like it doesn't look good. But the main concern is the durability of the reinforcement inside the concrete, and at the end of the day, the service life of your structure. But how to control it? So there are many different ways to control the shrinkage cracking, but here, because we are going to address the non-metallic reinforcement, first we are going to cover the steel reinforcement, how they use it, how it works, and then goes to and also explain the disadvantages of the steel, and then say why we are going to use FRP instead of steel. So to control the shrinkage cracking, the minimum steel reinforcement is typically designed and implemented. Nevertheless, the use of steel may not be suitable in environmental applications with the high risk of corrosion, or in places with a lot of freeze and thaw cycles with the colorides, and in those areas, the steel is not the best option. So we have to think for some other options. Here you can see some corrosion, and the corrosion is combination of the chloride and CO2 in presence of the moisture, which produce the corrosion of your steel reinforcement. These are not the rebars reinforcement here, but I mean, they're just some example of the steel corrosion that you can see every day on campus or in the street. Everywhere you can see all this corrosion. Okay, almost all of the metals and alloys are unstable in the Earth's atmosphere and will always be susceptible to corrosion. These are three aspects of the impact of corrosion on the society. The direct effects resulting in the injury or death in case your structure collapse or something, the contamination of the environment, and the financial cost. The overall annual direct cost of the corrosion were considered to be the additional or more expensive materials needed to prevent the corrosion damage. So you cannot use the steel anymore. If you want to prevent the corrosion, you have to go with epoxy coated steel or some sand coated rebars, or those stuff that can increase the initial cost. And then the labor for corrosion management, equipment required for corrosion related activities, loss of reliability, loss of capital due to corrosion induced deterioration, and the total direct cost of 5 different sectors is like $137.9 billion per year, and this number is for 2011. So now you may find some new number, but still it can give you an idea of the indirect cost. In addition, there are some indirect costs of corrosion, include plant downtime, the loss of product, environmental contamination, which can be direct and indirect, loss of efficiency, over design, user cost, insurance cost, and all those stuff, which can cause, I can say, a summation of $276 billion per year as a summation of direct and indirect cost of the corrosion. So as I discussed it before, we have many different no, I didn't mention this. So we have different alternatives for the steel to prevent the corrosion. You can use different concrete mixture. You can have concrete surface sealers. You can increase your cover. You can use better curing techniques, corrosion inhibitors, stainless steel, epoxy coated, and at the end, last but not least, the fiber reinforced polymer reinforcement, which is our main interest here. But all these alternatives have different disadvantages. For example, changing the concrete mixture may compromise other desirable material properties such as compressive strength, workability, your slump, and other stuff. In addition, if you want to use concrete surface sealers, it may help prevent some aggressive substances from getting into the concrete, but its overall effectiveness due to the literature is a kind of questionable. In addition, increasing the concrete cover makes it take longer for the coloride to reach the steel, because you have a very thin layer on top of your steel reinforcement, which is not stable in the presence of the coloride. So when the coloride goes inside, so you will lose that thin film on top of your rebar, and the rebar will start to corrode. So if you increase the cover, it takes longer for the coloride to reach the steel reinforcement, but the penetration of the corrosive substances depends more heavily on the crack width than the crack depth. So even if you put your rebars in a lower level, at the end of the day, still you have the corrosion, maybe 1 year later, maybe 2 years later, but still you have it. And despite the benefits of stainless steel, which is another alternative, a major setback which prevents wide application of the stainless steel reinforcement in structures is the high initial cost. So, maybe there are a lot of contractors that they are not interested in spending a lot more money as the initial cost. And I do not blame them, because it's a combination of safety and the economy. The alternatives should make some sense to them. To this end, to make applications such as horizontal constructions, as I mentioned before, the slab-on grades, more durable and sustainable, the use of non-metallic fiber reinforced polymer, which we call them FRP, the rebars and meshes as the secondary reinforcement can successfully address the shrinkage cracking challenges. The FRP rebars are suitable alternative to steel, to epoxy coated steel, stainless steel, in different applications that your concern is the durability, or you need magnetic transparency because they're fibers, right? Or you need ease of demolition for the temporary structures. You have some structures that they are not permanent. You want to destroy them very soon, and you need something that you can destroy it easier. The so-called FRP composite materials offer several advantages with respect to traditional metallic materials. Their innovative properties, such as high tensile strength, high tensile modulus, lightness, corrosion resistance, electromagnetic transparency, and the possibility to engineer the mechanical properties by changing the composition. I mean, if you change the fiber type, if you change the resin type, if you change the fiber content, all this stuff, you can come up with a new material that has different characterizations. But by the way, I'm not here to say there is no issue with the FRP. I'm here to say we can address those issues. FRP has several issues, but we can address them. We can find the applications that we can use the FRP without any issues. But currently there is a lack of information and prescriptive guidelines based on empirical evidence. So because you cannot just go out and there and say, okay, let's use FRP instead of steel. So we need some proof, some test results, and I can say some empirical evidence to specify the adequate levels and configurations of the secondary fiber reinforced polymer reinforcement. Let's go to the next slide and talk a little bit about the sustainability. Actually, in sustainable construction, that is our main concerns, and we are going to replace steel with FRP, is in sustainable construction, technologies and material systems are developed to last longer, consume lower energy, and emit less carbon dioxide. The majority of applications utilize FRP rebars to mitigate the risk of corrosion in concrete structures that operate in aggressive marine environments or are exposed to de-icing salt, which I mentioned before. The service life of these types of structures is strictly contingent with the durability of the internal reinforcement. And okay, and I mentioned all those stuff about the initial cost, but the environmental impact may be slightly higher than those of the conventional steel in terms of maybe CO2 emission, but the use of FRP rebars in concrete structures subject to a harsh environment can really increase your service life. And at the end of the day, you may see that you spend a little bit more at the first, but now in terms of the life cycle analysis, you see that you have a better performance, you're spending less money, you need less maintenance, you need less repair. So, and there are some research there that here I have a table which shows that in some applications they use FRP with, 100% replacement. So they had 43% decrease in the global warming in terms of the CO2 emissions. And there are many other things here you can see in the table in terms of the CO2 emission, the energy consumption. But as I told you before, we need some specifications and some codes to prove that we can use these FRP materials. In the United States, where the power to regulate constructions is vested in local authorities, a system of model building codes is used. And in this model, anyone can submit a code change proposal, but they need to say what is the reason for the change, the description of the change, and the supporting material. So to prove their claim. And the alternative materials, designs, and method not specifically addressed in the code in IBC that can be approved by the building officials when they comply with the intent of the provisions of the building code in IBC or maybe IRC. In terms of their quality, you should say that the quality is the same or even better than the conventional materials that are in the codes. The strength, the effectiveness, the fire resistance, durability, the structural safety, and maybe some other parameters. Here we have some documents that we call them the acceptance criteria. An acceptance criteria is developed when an application is received for an ICCES report. ICCES is the International Code Council for Evaluation Service. On a product that is an alternative to what is specified in the code, and there is no existing criteria that would apply to the product. So it's a new one, they don't have any idea, so you have to prove something. And acceptance criteria may also be developed when the codes are not clear in a particular area or on some specific issues related to that new product or even the previous product. When the industry raises the concerns regarding the report requirements, or when a new criteria is deemed necessary by the report applicant, or for example, the ICCES staff or the ICCES evaluation committee. And here, why we are talking about the AC521. AC521 is a acceptance criteria for fiber reinforced polymer bars and meshes for internal reinforcement of non-structural concrete members. And actually the slabs on ground or slabs on grade, they are not really structural applications. They are non-structural applications. And if we want to prove the effectiveness of our FRP rebars, we need to comply with this with this acceptance criteria, which is number 521, which covers several tests to evaluate the bars and meshes in terms of their physical and mechanical properties. These tests should be included in the evaluation report of each product to be compliant with the AC521. Here we have several tests in terms of the physical properties, such as fiber content, the mean glass transition temperature, which is related to the resin that we use as a matrix to keep the fibers together, and also transfer the stresses from one fiber to another one, and the mean degree of the cure, and etc. In addition, there are some mechanical properties testing covered in this AC, in this acceptance criteria, such as the tensile test, the pull-out test, transverse shear strength test, and the last item in the table, I mean here, not the table here, I mean in the slide, is the shrinkage cracking test, which is not clearly addressed, and we're working on it to add some more science on it, come up with the test method that everybody in all labs, they can do the test and come up with the result and evaluate their products. Now I'm going into really what we are doing in the lab in terms of the evaluating plastic and drying shrinkage. In this test, we are evaluating the plastic and drying shrinkage of the concrete that is reinforced with the fiber reinforced polymer compared to the conventional steel reinforcement, and both they can be rebars and also meshes. And we are going to demonstrate the equivalent or better performance of the FRP in comparison to the steel. So we have to say it's at least perform as the steel, so we can replace it. We have started with general guidelines of the ASTM-C 1579, which evaluate the plastic shrinkage of the FRC, which is a concrete that you have the fibers inside the mix. It's not the rebar or reinforcement. It's just some fibers. You can put them inside your concrete mix, as you have your sand, you have cement, or everything in your concrete. So there are some fibers, and we call them FRC. The general guidelines, such as the conditions of the restraint, moisture loss, concrete clear cover. Actually, we made a lot of changes to come up with the specific test method to evaluate the shrinkage in FRP reinforced concrete. And here, the overarching goal of this work is to provide empirical evidence, as I told you before, some empirical evidence to evaluate shrinkage cracks in these specimens by comparing the FRP and steel side by side in the same mold, in the same wind tunnel. Later, I will cover what is our wind, what is the wind tunnel here, what is the size of the specimen, all those stuff. In this ongoing research, hopefully at the end we will define a minimum FRP reinforcement requirement, and that can be verified the spacing and the minimum area, so that the minimum requirement can be a combination of the spacing and the minimum area of the reinforcement. We have the same thing for the steel. So here, for those of you who are studying in structures and you have a degree in civil engineering, you know that there is a very popular, I can say very famous number, which is 0.0018, which is the minimum requirement for temperature and shrinkage reinforcement using a steel rebar. So we are going to do the same thing for the FRP, and maybe we need some changes for the steel as well, because some of our research shows that numbers maybe are not really reasonable. Maybe we are going to change those as well. But after investigating the shrinkage phenomenon with our specific design of a specimen and the wind tunnel, the environmental conditions, everything, at the end, a reliable and repeatable test which determine the shrinkage crack control of FRP and also the steel reinforcement will be developed. So at the end of the day, hopefully, we can standardize our method as an ASTM test protocol, or maybe as an appendix to the previous ASTM, which was the ASTM C1579. Here you can see the details of the specimen. Here I do not have the dimensions, but the slab is like 4 feet by 3 feet by 4 inches, the depth. We introduced some restraint and the riser inside the specimen to force the concrete to crack. You know, because in shrinkage, if you let your concrete to shrink, I mean, all the parts shrink together. At the end, you will not see any cracks because you will not see any. You do not have any stresses because you need some restraint to limit your concrete and have different shrinkages in different parts to develop the stresses. And when the stresses exceed the tensile stress of your concrete, you will see those cracks. And then you can study the cracks, because here we are going to say that FRP is performing better or even perform equal, but how? With comparing the crack widths, crack depths, I don't know, even crack area, crack length, and at the end say that, okay, they are performing the same, or even the FRP is doing a better job. And yeah, let's go to the next slide. Here's the test setup. In the pictures, you can see our the setup in the same slab. In one side, we have the FRP, and in the other side is the conventional steel. And the wind tunnel in the photos in the right, which helps us to make a laminar airflow on the surface of the concrete to accelerate the evaporation rate of water, which is critical in plastic shrinkage, and make the conditions severe enough for the crack. And the reinforcement, here we have to understand that if we don't see the cracks, we are trying to make the conditions severe, because if we don't see the cracks, we cannot compare them together, because this temperature and shrinkage reinforcement do their jobs after the concrete cracks. Before the cracks, they are not doing, I can say they are not doing anything. So when the cracks shows up, they start keeping the cracks together. And when they can keep them tight enough, you will not have the penetration of the colorides or other chemicals inside your concrete, which is our goal. Okay. Okay. There are many parameters which affect the result of this study. These variables are classified in different classes: environmental variables, material characteristics, and also the workmanship. The first class of the variables includes wind speed on the surface of the concrete, relative humidity, ambient temperature, and to be honest, it's very hard to control them in the lab. Outside is impossible, and also in the lab is still a pain in the neck. And the same class contains the characteristics of your materials, your rebar, and also, I mean, your reinforcement, and also your concrete, the cement content, the fiber content in the FRP, the water to cement ratio, the aggregate size, admixtures, supplementary cementitious materials, concrete temperature, fiber types, rebar surface profile. And each rebar has a different surface, ribbed or sand coated, or different surface profile, which we cover it in the second study in this presentation. And also each rebar has different modulus of elasticity that can make some changes in the result. And in terms of restraint conditions, as I told you before, what actually caused the shrinkage cracking is the restraint, which doesn't let the concrete to shrink with the same amount at all points in the depths and in the lengths of the concrete. If the entire slab shrinks together, there will be no cracks. With restraining, you will cause the stresses exceed the concrete tensile stress and make the cracks actually. And also we have something, we call it the stress concentration. I think all of you are familiar with that. We are providing a riser at the mid-span. Let's go back to the this slide here. You can see we have two restraints in the side. There are some T-bars, but they are smaller. We have another one. Those guys are the restraints, but the one at the mid, which is higher than the other, is the estrus riser. Okay, let's go back here. And what is the role of that estrus riser? That forces the crack to occur in the desired location by a sudden change in the cross section and making a weak area at the mid-span. So in that area, you will have a smaller amount of concrete that can cracks earlier. And if we don't provide the riser, we may see small cracks, the map cracks in different sections that make the investigation more complicated. So you have to monitor the entire section, you have to do several measurements, and at the end of the day, because when you have cracks everywhere, so you cannot, you will have a kind of, I can say, estrus release in different parts that cause more cracks, but tight cracks. So it's better to have something at the mid-span, which is wider, you can study it better, and also you can compare the results better. So because I mean, you can see the difference better. And also, as I told you before, the workmanship can really change the result in this project, because there are many variables affecting the result. So the workmanship, even as I told you before, even finishing the surface of the concrete can change the result here. And what we have done in terms of the quantification of the cracks. Here you can see some photos of the crack depths and crack widths, crack lengths, all those characteristics of the cracks. In each slab, each slab is divided into two parts. It's better to say two parts. One part is reinforced with the FRP, one part is reinforced with the steel. And why we have both of them in the same mold, but we have a divider at the mid-span, because we wanted to have both a specimen in the same wind tunnel. We wanted to expose them in the, in the same environmental conditions in terms of the wind speed, the relative humidity, and also the temperature, the ambient temperature. So it was very important to put them in the same mold. And also each part, as I told you, one part is FRP, one part is steel. Each part is divided into 5 sections to capture the photos for the image processing. The image processing software is used to measure the crack width, length, and the area. And in addition, we had some cores to make sure that the reinforcement are engaged, because if you have just some superficial cracks, you cannot say that, okay, it's because of the effect of the rebars. The rebars are doing very well, so we have smaller cracks. But no, we should see the penetration of the cracks and make sure that the rebars are engaged. For example, in this case, in the core that you can see here, it's almost penetrates half depth of the slab, and the slab was almost 4 inches. So I assume that it penetrates 2 inches, and the rebars are in the depth of 3/4 inches. So for sure, I can say that the rebars are engaged. And the crack quantification is done by the image processing techniques, as I mentioned before, to measure the widths, lengths, and area. Actually, there's a formula. We call it the crack reduction ratio, which is defined in the ASTM C1579. But we had to make some changes for this test, and which shows the performance and the effect of using FRP reinforcement instead of the steel. So we ran several tests here. Just I want to mention one of those tests. In one of them, we had the GFRP, which is the glass fiber reinforced polymer. It's one type of our reinforcement. And in the other side, we had the conventional steel. Both of them were number three reinforcement, which is the diameter of this reinforcement is 3/8 inches. and also the spacing between the rebars was the same and was 12 inches, the spacing between the rebars. At the end, after the image processing and using the CRR formula, we come up with the result that the GFRP specimen was more effective than the steel with 16.7%. But still, we need to run many more tests, because with one test you cannot say that, hey, we proved it. So still some more tests need to prove our claim. And here I want to mention a piece of advice for other researchers and for other graduate students. Please watch around in your institute and the labs around. There are many equipment that you can use and reinforce yourself with new skills and enrich your dissertation with some innovations. In my first study, which was the shrinkage study at the University of Miami, we were struggling with rebars implementation. The concrete cover in this study is critical and an effective parameter. So it was very important to make sure that the rebars are in the depth that we want. But I'm not sure if you have ever tried to implement rebars in the concrete. There are some plastic and steel chairs available in the market, but you know, they have like a specific depth, which was not appropriate for us. Every time we had to grind them, we have to cut them and put them beneath the rebars and make sure that they are working. And it was a really pain in the neck. Each time we wanted to cast our specimens for 3 slabs, we were spending like 3 days just to implement the rebars. You know, 3 days was really hard. The resources in the lab are limited, so we have several staff, but they're working on different projects regarding the priority of those projects. So we had to save the time. So finally, to satisfy the requirement of the AC 521, we needed an appropriate chair with the height of 2 inches and 5/8 inch based on the specimen geometry, rebars diameter, and the thickness of the steel plate, which we used to attach restraints and the riser on it. When it comes to practice, you may see that the 2 and 5/8 inch will not satisfy the requirements in all sections because of the mold and steel plate imperfections. I don't know, the bend in the rebars or whatever. At the end, you cannot use the same, the same height chairs in all sections. So we came up with an adjustable chair design, and the Johnson & Johnson collaborative lab at the College of Engineering at the University of Miami helped us to print an adjustable chair. Using this adjustable chair, we are saving a lot of time and also our mental health. So yeah, just I wanted to mention this as a part of this presentation. Just look around for all the equipments you have in your institute and try to help them. There are many people, many good people try to train you and help you using those equipments. So I want to wrap up the previous study about the shrinkage, and I'm going to the second project, which we have recently started working on it, which is the surface profilometry of the FRP rebars, the non-metallic reinforcement, which is a collaborative research with the University of Sherbrooke in Canada. And this research is the second leg of my dissertation and is characterization of the FRP rebar surface profile and find the relationship between the geometrical ratios, surface roughness, and finally the bond behavior, which is an important concern in reinforced concrete. We have 5 different surface profiles. I mean, surface enhancement, which is the first let's define the surface enhancement. The surface enhancement is the treatment applied or created during the manufacture of the FRP reinforcing bars, or also in steel bars. We have this, almost the same thing. In several forms. I mean, you can do the sand coating, you have the spiral winding, you have the machine grooves, or other methods, or a combination. For example, we have some rebars that they are sand coated and also they are helically wrapped. So they have deformation and also they have the sand coating. So we have 5 different surface profiles in this study, and with 2 different diameters. They are number 5 and number 8 bars. In this study, we will consider the surface enhancement. We will measure the geometrical ratios, the surface roughness, bond behavior, the materials characteristics, which can really affect the entire result. And yeah, okay. In terms of the bond and the surface profile, you can say a bar surface deformation or the texture is induced so that the mechanical bonding is developed between this deformation and the texture can affect your mechanical bonding, which develop between the fiber reinforced polymer rebars and the concrete. So this study will investigate the minimum roughness requirement for FRP rebars to guarantee the requirement of the bond strength. So because we have different surface enhancement, so we should use different factors for each of them. But if we can correlate all of this surface enhancement to a parameter, which is the surface parameters, the surface roughness, so we can say that, okay, you do not need to just go to the code and check that if it's the sand coated, is it the deformed, is it the grooved one, what is the type, and come up with the bond behavior. So just you can use the surface roughness and characterize all of your surface enhancement. But now it is unclear how the surface roughness can affect the bond behavior in reinforced concrete structures. In addition, having different surface types doesn't let us to work with the same KB factor for all rebars that has a minimum required characteristics that can satisfy the desired bond behavior. There are several equipments and several approaches that can help you to characterize the surface of your materials, in this case the rebars. The first one I can mention here is the linear contact-based measurement, which is the typical measurement system, only provides measurement data on the areas that they are able to contact, because the probe tip should contact your specimen, and measuring the specific locations where to put the probe makes the result unreliable, because there are some places that you can put your tip on them. There are some places that the roughness is very small, so the result is really depend on the tip. And also the data is limited to the points and the lines, and that's the main problem with this linear contact-based surface profilometer. So to address this problem, one way is to do several linear measurements. For example, choose a 2 millimeter by 2 millimeter area between for example, between two logs of your reinforcement, and do several linear measurements. For example, every 10 microns, do one measurement and go to the next line, and at the end, with omitting all the noises in the data that you receive from your surface profilometer, you can build the 3D topography and say, okay, here is my surface profile, and you can compare different type of the rebars together and come up with the surface roughness parameters. But there are other equipments that hopefully we are going to use them. We are trying to consult with the company to use a 3D optical profilometers, which has a higher precision. It can measure the entire surface in 1 second. So you do not need to do several measurements every 10 microns. Is crazy. So it can do it in 1 second. The results are accurate. You can repeat them easily, very fast. It can give you the profiles, the dimensions, the roughness, which is our main concern here, and also the volume and the area measurements. And the volume and area measurements can help us in also the sand-coated rebars, because in the sand-coated rebars, the roughness is important, and also you should have an idea of your particle size, because you should know that what is the maximum and minimum sand particles on the rebars. And unfortunately, we cannot have those sand particles limits from the manufacturer, because it's kind of secret for them. So we have to figure it out ourselves. So this device can help us in all these measurements, and also it can give us some statistical analysis to compare that 5 different rebars we have in this study. And also, in addition to the in addition to the surface profilometers to come up with the surface roughness, there are other parameters that they are important in the surface profilometry than the roughness. They are the geometrical ratios like the concrete log ratio, or I mean the rib height, the rib area, or all those stuff. And also these are for the deformed bars. I mean for the grooved one, for the helically wrapped, all those stuff. But in the sand-coated bars that we call them non-deformed rebars, the particle size is very important. So we are trying to use the digital microscopes to have a better visual inspection and also better understanding of the surface profile, to really understand what we have on the surface, how is the change in the surface. I mean from the log to the flat surface. And also the particle size. So in this digital microscope, there are some functions that help you to measure your particles, but still it's time consuming. So for that one, we have another approach that later I will cover it. But here the digital microscope help us to measure the geometrical ratios that can really affect the bond behavior, which is the main purpose of this study. And here there's another thing that I'm going to mention for the particle size distribution and the limits. So there, we have another device, which is we call it microtrack, which is the particle size analyzer. So it can help us to characterize and also measure the particle size limits and the distribution. And for this test, what we do is first we have a fiber content test for the rebars. We put the small piece of the rebars, for example, 1 inch in the oven. We'll try to burn out the resin, and at the end you will have just the sand coat. I mean the sand, if the rebar is sand coated, and also you have the fibers, so you can easily take out the fibers, and at the end you will have just the sand particles. And using this sand particle analyzer, we can measure all those particles. And here it's a measurement which I have done maybe 1 month ago for a sand coated rebar, which shows the particle distribution. You can see two normal distribution besides each other, and what is the smaller peak and what is the higher peak, because as in the resin, they do not really use the net resin. So in the resin you have some other particles that they are not the sand. The sand are on the surface and they are larger, but there are something in your resin which are some particles. They are not sand, but when you put the entire thing inside the particle size analyzer, it will give you the entire thing. So we can just consider that part as a noise. And if we have those limits for the particles in the resin, we can just omit them and come up with the particle size distribution of the sand, which can give us a better idea of the surface roughness. And here I was presenting on behalf of a team. Without their help and support, it was not possible to conduct this research. All the colleagues and friends at SML, I mean the Structures and Materials Laboratory, the J&J collaborative lab here at the UM, and also my advisors, the lab coordinator, my advisor, lab manager, everyone, they really helped me to come up with this. Even they are not completed research, but this ongoing research, they really helped me, and just I was their representative to be here and present the work. And also here I want to thanks to Dr. Sorani and Dr. Pestana for giving this opportunity to present my work here, and also thank to all the attendees. And now I think I can say the floor is open for the Q&A.